Okay, let's unpack this. What if the buildings around us weren't just, static structures? What if they were more like dynamic, intelligent entities,
Yeah.
constantly adapting, evolving based on their environment, maybe their purpose, even our preferences? Imagine a world where instead of meticulously drawing every single line and curve of a building, you could essentially teach a computer the rules that would then generate the building itself. What kind of architectural freedom, what kind of mind-bending complexity might that unleash? Well, today, we're not just imagining it, we're diving headfirst into that reality. We're exploring the fascinating world of parametric design and computational modeling. Our mission in this deep dive is to explore this really advanced design process. We want to understand how architects and engineers define a set of parameters and rules. These rules allow computer algorithms to generate an almost infinite range of complex geometric forms. Think of pioneering firms like Zaha Hadid Architects or maybe Gary Partners. Their signature fluid, dynamic buildings, they just wouldn't be possible without these tools. We'll unpack how these parametric models aren't static blueprints. No, they're more like living systems. They can be instantly updated to respond to new inputs, like, say, changing sun angles or evolving structural requirements. We'll connect this revolutionary design method to the rise of digital fabrication, revealing how these really intricate forms can often only be brought to life using computer-controlled machines. And we'll also explore the cutting edge of generative design. That's where AI gets used to discover thousands of potential design solutions. And of course, we'll have to delve into that ongoing debate. Do these powerful tools enhance or diminish the role of the human designer? This is really a look at the absolute frontier of architectural design. It's a practice it's part computer science, part mathematics, and undeniably part art.
That's such a crucial way to frame it, because this isn't just a new drafting technique, you
Yeah.
know?
Mhm.
It's not just a fancier way to sketch. It's a fundamental philosophical shift in how we actually approach creation. We're moving away from static geometry, fixed shapes, fixed forms towards dynamic, rule-based systems. It's about defining relationships, defining behaviors, and allowing complexity to sort of emerge from simple, maybe even elegant rules. This practice really blends the precision of computer science, the logic of mathematics, and, the boundless creativity of art into something, well, something mind-bendingly powerful. It's a profound rethinking of the entire design process. The designer becomes less of a sculptor, maybe, and more of a system architect.
Now, you might think this whole idea of rule-based design, this algorithmic approach, is strictly modern, like something born in the last few decades with computers. But the truth is, architects have been working with incredibly strict, predefined rules and proportional systems for centuries. It's actually an ancient legacy, deeply embedded in the history of building. When you look back at classical architecture, for instance, the adherence to rules was absolute. It was almost like a form of architectural code, really. Consider Vitruvius. His famous work, 10 Books on Architecture, it's a foundational text, right? But it isn't just commentary. It's more like a detailed manual. He laid out incredibly precise mathematical measurements and relationships for pretty much every architectural element you can imagine. From the subtle curve of a pedestal's base, which was designed, by the way, to subtly counter optical illusions, all the way up to the majestic proportions of the columns themselves, and then the intricate layering of architraves, friezes, and cornices that crown a building. He detailed these elements with such specificity, it's almost like an instruction set. How a column shaft might taper, the exact dimensions for its base and capital. This wasn't just guesswork, it was a highly organized, systematic approach. He even meticulously outlined specific rules for different temple types, like the antis, which was fronted with pilasters instead of freestanding columns, or the protilos, featuring columns only at the front facade. And then for those with columns at both the front and back, the amphipotilos. These weren't just loose guidelines, you understand. It was a rigorous, almost algorithmic architectural language. It left very little to chance, ensuring consistency and adherence to established ideals.
Right. And if we connect this to the bigger picture, what we're really seeing in ancient architecture, particularly with someone like Vitruvius, is, well, in a sense, it's a very sophisticated, albeit manual form of parametric thinking. Ancient architects weren't just drawing shapes. They were defining clear parameters, maybe the column diameter or some kind of module unit, and then applying a really strict set of relationships and rules. The resulting forms then adhered to those rules rigorously. That ensured aesthetic harmony, structural consistency, and importantly, cultural resonance. Imagine having a sort of master rule book where changing one fundamental dimension, let's say the diameter of a column base, would systematically dictate the dimensions of the capital, the whole entablature above it, maybe even the spacing between the columns. And Andrea Palladio, another master from the Renaissance, he absolutely continued this tradition. He provided incredibly granular instructions in his own work, like his inventive solutions for buildings in Venice. He'd specify exact ratios for an architrave's parts, defining how it related to the frieze and the cornice, or precisely how a capital should relate to the column's diameter, like half the diameter, divided into 3 parts. He integrated classical orders, Ionic, Corinthian, composite columns with specific room dimensions, yet he still managed to adapt these systems to site-specific needs. That shows a powerful kind of rule-based adaptation, right? It allowed for both adherence to principles and a certain contextual responsiveness. These masters understood that design could be systematic, deeply systematic, even if their tools were entirely manual.
That's such a compelling way to look at it, a manual parametric system. But, despite the elegance and the historical weight of these systematic approaches, there was always this underlying longing for new forms, a desire to break free from what some people perceived as, well, dogma and rule of the dead. This yearning for architectural innovation is a recurring theme throughout history, and it often leads to powerful critiques of monotony. Consider the observations of Eugène Viollet-le-Duc. In his lectures on architecture, he talked about symmetrical buildings that, to his eye, just reproduce hundreds of times the same columns with the same capital, the same window with the same architrave for nearly a mile in length. He pointed out quite astutely that the public would eventually weary of passing these miles of monotonous architecture. This wasn't just about style preference. It was a profound unease with static, repetitive design that maybe lacked vitality or responsiveness. He saw it as, well, stifling genuine architectural expression. And this growing desire for change, this call for an architectural revolution, it really culminated in declarations, maybe most famously articulated by Le Corbusier. In his seminal work, Towards a New Architecture, he proclaimed almost militantly that construction has undergone innovation so great that the old styles, which still obsess us, can no longer clothe it. For him, it was a seismic shift, irreversible. He asserted that all the values have been revised. There's been revolution in the conception of what architecture is. Le Corbusier basically believed that the old architectural code, with its thousands of years of rigid rules and regulations, was just, well, no longer relevant. It wasn't capable of expressing the spirit of the modern age. He was pushing for a complete reevaluation, a fundamental change in how we even think about and create buildings.
This really raises a profound question, doesn't it? How do architects innovate? How do they find new expressions when the traditional methods, the established dogmas, are perceived as insufficient, maybe even stifling? This historical tension, this kind of push-pull between strict rules and the desire for radical freedom, it directly sets the stage for the computational tools we see emerging today. It echoes the insights of Louis Sullivan, in the autobiography of an idea. He spoke of the great modern inversion. He believed that dogma and rule of the dead are passing, making way for a philosophy that becomes more human, immersing itself in the flow of life. Science pushing back specters, as he put it. He envisioned a future where architecture would move away from these rigid, inherited forms towards something more authentic, more responsive, deeply connected to human aspirations. So this quest for freedom, maybe paradoxically, now finds its most advanced expression not in abandoning rules altogether, but in defining entirely new kinds of rules, rules that are digital, dynamic, and incredibly powerful.
That historical context is absolutely crucial, because it shows that the underlying idea of rule-based design isn't new at all. But now let's fast forward to something truly groundbreaking. Here's where it gets really interesting. How do we bridge that gap? How do we get from those ancient manual rule-based systems to something that feels genuinely revolutionary in its speed, its complexity, its sheer generative power? The answer, in large part, lies in the digital age, specifically with tools like building information modeling, or BIM. And BIM is far, far more than just 3D modeling. You have to understand that. It's best understood as an integrated project delivery (IPD) process. It fundamentally redefines how projects are managed. It fosters truly effective collaboration among all the stakeholders, owners, designers, contractors, right from the very earliest design stages, all the way through construction and project handover. This is a clear, decisive break from those traditional linear processes. The ones that historically relied on fragmented, paper-based information exchange. Always out of date, always causing coordination headaches. With BIM, the entire project team works together, using one interconnected digital model. This allows for a holistic, often real-time evaluation of crucial trade-offs. Things like cost, energy performance, Structural integrity, functionality, aesthetic appeal, even the nuances of constructability can actually be built efficiently. All of this can be assessed and optimized pretty much simultaneously. It ensures owner requirements are met, often with significantly reduced time and cost. It's a dynamic, integrated ecosystem where information isn't just passed along linearly. It's shared, continuously updated, and instantly accessible to everyone on the team.
That's a crucial distinction, you're right, because BIM creates this digital ecosystem where every single element isn't just a geometric shape on a screen, it's intelligent. It's interconnected, it carries embedded data. It's not simply a drawing, it's a living database. It's a powerful simulation tool, it's an advanced coordination engine. And this foundational shift is what lays the essential groundwork for truly dynamic design. Designers are no longer working with static lines and surfaces. They're interacting with objects that carry embedded information, their material properties, their structural behavior, their cost, energy performance, and importantly, their behavioral rules. This intelligent, dynamic interaction is the very heart of parametric design. When changes to one element automatically propagate throughout the entire model according to those rules.
Exactly. And building on that point about embedded intelligence, a core strength of BIM tools lies right in their innate parametric capabilities. This means they can adapt and change designs parametrically, which is just an absolute game changer in terms of efficiency and responsiveness. It leverages deeply embedded engineering knowledge built right into the software for more rapid design development. Ultimately, this allows design teams to satisfy client needs and explore complex options far more efficiently than ever before. I mean, think about it. Instead of manually redrawing hundreds of elements every time a key dimension or material changes, the model just instantly updates. Everything recalculates. It dramatically accelerates the design process. It makes it possible to consider many, many more alternatives in the same amount of time. There's a great example in the BIM handbook. Precast concrete estimator, using a BIM tool not just to visualize, but to swiftly develop, optimize, and even sell a complex parking garage design. They can adjust parameters like floor height, column spacing, or material thickness, and the entire structural system, the cost estimates, the fabrication details, they all update in real time. That provides an incredibly persuasive and efficient design-build solution. And to really drive home the impact of this, think about how specialized BIM design applications have been developed specifically for modeling at highly detailed fabrication levels. These tools provide different object families. They're essentially libraries of intelligent components for embedding diverse types of expertise right into the model. This facilitates everything from materials tracking and plant management systems all the way to fully automated fabrication. Let's look at the history a bit. Early steel fabrication packages like SDS2, Tekla Structures, and AceCAD Strucati, they started as robust 3D layout systems. They incorporated predefined parametric object families for connections and editing operations, simple enough, but they rapidly evolved to support automatic connection design based on applied loads and member sizing. And critically, they linked directly to computer-controlled cutting and drilling machines on the shop floor. This seamless integration makes them an indispensable part of automated steel fabrication today, ensuring incredible precision and efficiency.
Yeah, and if we connect this to the bigger picture, this capability defining components parametrically and embedding intelligence directly within them is just a monumental leap from the static blueprints of the past, a completely different world. It allows for highly complex parts to be designed, coordinated across multiple disciplines, structural, mechanical, electrical, and modified with unprecedented accuracy and speed. It's not just about drawing faster, it's about building in the logic and the intelligence of construction right from the very outset of design. This drastically reduces errors, reduces rework, and enhances constructability, especially for intricate designs that might have been too risky before. And importantly, this isn't limited to steel. We see similar parametric systems now widely developed and utilized for precast concrete, reinforced concrete, sophisticated metal ductwork for HVAC, complex piping systems. This widespread adoption really shows how this fundamental shift impacts multiple building systems, ensuring precision, reducing waste, and enabling the efficient realization of increasingly complex architectural visions.
Okay, so we've talked about the historical roots of rule-based design, right? And how BIM provides that crucial digital foundation. Now let's explicitly define and expand on what parametric truly means for the actual design process today. It's a crucial distinction because it's really about designing a system that generates a building, rather than just designing a singular, fixed, unchangeable object. At its core, parametric design means that instead of drawing fixed geometry, like a wall or a window with set dimensions that you just type in designers, define a set of controlling parameters and rules. Think of parameters as the variables: the height of a floor, the angle of a facade panel, the spacing between columns, maybe the material thickness. The rules are the relationships or the algorithms that determine how those variables interact and change to generate the final form. For instance, a rule might state that the facade panel's angle is a function of the sun's position throughout the day to minimize heat gain. Or maybe the column spacing must adapt to structural loads calculated in real time while maintaining a minimum clear span for usability. The computer then generates the geometry dynamically based on these definitions. It's like creating a flexible blueprint or maybe a sophisticated recipe where changing one ingredient or one condition automatically adjusts everything else according to your predefined rules. This is exactly how firms like Zaha Hadid Architects achieve their signature fluid, not repetitive forms. They're not drawing each individual curve, they're defining the system of curves, of the logic that generates them.
That's a perfect analogy of this idea of a recipe for form. It really brings up an important question, though. How do you actually translate complex design intent, your artistic vision, your functional requirements, into a system that the computer can understand and generate from? It's almost like writing a sophisticated code for a building to assemble itself, responding to its environment and its own internal logic. Donella Meadows, in her brilliant work, Thinking in Systems, provides a really fundamental definition. She says a system is a set of things, interconnected in such a way that they produce their own pattern of behavior over time. Now, in parametric design, these things are the architectural elements, walls, windows, structural members, whatever, and their interconnections are precisely those parameters and rules we just discussed. The beauty of this approach is that from a single conceptual framework, a single set of core rules, you can generate a vast range of outputs. You can explore countless design variations simply by adjusting those initial parameters. It offers immense creative freedom, but it definitely demands a different kind of thinking from the designer. You're moving from drawing shapes to defining relationships and behaviors.
And this leads us to one of the most powerful aspects of parametric models. They are inherently dynamic. They are not static. They're like living systems that can be instantly updated and regenerated in response to new inputs or changes in parameters. This isn't just a minor convenience, it's a fundamental paradigm shift in the design workflow. I mean, imagine designing a building where its facade can automatically adapt its opening sizes, or maybe the angles of shading devices based on changing sun angles throughout the day, optimizing for daylighting while minimizing unwanted heat gain, all automatically. Or picture a structural system that instantly recalculates its requirements when a different material is specified, or when snow loads or seismic forces are updated in the model. These models can even respond to real-time environmental data, just as Meadows described natural systems being buffeted, constricted, triggered, or driven by outside forces. This dynamic nature allows for incredibly rapid iteration. You can explore countless design alternatives and optimize in real time against various performance criteria, whether it's structural efficiency, energy consumption, cost, or even things like visual permeability or acoustic performance. It allows designers to rapidly test ideas that would have taken weeks or even months with traditional methods. It fundamentally transforms the speed and the scope of the design process.
What's fascinating here, and also critically important to understand, is the power and the sensitivity of the feedback loops within these dynamic systems. As Meadows eloquently points out in Thinking in Systems, system behavior is particularly sensitive to the goals of feedback loops. What does that mean? It means if the goals of the specific indicators of satisfaction that you build into the rules you define, if those goals are inaccurately or incompletely established, the system might just obediently work to produce a result that is not truly intended or wanted. Think about it. A system might efficiently optimize for, say, minimal material use, which sounds good. But if you haven't also specified aesthetic quality or maybe ease of construction or occupant comfort as equally important goals, you could end up with a structure that's structurally sound but visually unappealing or impossible to build or uncomfortable to be in. This highlights the critical, absolutely essential, overarching role of the human designer. We're not just setting parameters, we're essentially defining the intelligence and, crucially, the ethical objectives of the entire system. We need to be acutely wary of what Meadows calls rule-beating traps, or seeking the wrong goal traps. These are situations where the system, left unchecked, might game the rules or achieve a narrowly defined goal at the expense of the overall holistic purpose of the design. The designer's deep understanding, their foresight, their holistic judgment, these are still absolutely paramount in setting the right parameters and articulating clear, comprehensive objectives for the system to follow.
Okay, so you've designed these incredibly intricate, dynamic forms on a computer. Forms that can twist, curve, adapt in ways that traditional drafting just never allowed. And remember, these aren't just pretty pictures. These are intelligent, data-rich models. But the big question is, how do you actually build something that might completely defy conventional construction methods. This brings us to the absolutely essential link between parametric design and the world of digital fabrication. The reality is many of the complex geometric forms generated through parametric design would be incredibly difficult, if not outright impossible, to build using traditional manual methods. Imagine trying to fabricate the intricate, non-standard curved panels of a building by Gary Partners, or the fluid double-curved surfaces you often find in Zaha Hadid's work. The level of precision required, the sheer volume of unique, non-repeating components, the incredible amount of skilled labor involved. It would be prohibitively expensive and probably be very prone to error if you were relying solely on conventional static drawings and craftspeople working alone. Digital fabrication, therefore, becomes not just an advantage, but an absolute necessity for bringing many of these ambitious designs into the physical world. It's the critical, often seamless bridge from the digital bits of the design model to the physical atoms of the constructed building. Without it, many of today's most ambitious architectural projects, the ones that really push the boundaries, would simply remain purely conceptual. They'd stay on the computer screen.
Right. And this raises a fascinating and crucial question. How exactly do these evolving bits, this complex stream of digital information, translate so seamlessly and so accurately into physical atoms? Neil Gershenfeld, who's a real pioneer in this field, talks about this in his book Designing Reality. He describes it as allowing evolving bits to arrange atoms and vice versa. This concept describes that direct computational link, that pathway, from a parametric design model straight to the computer-controlled machines that fabricate the physical components. It's about creating a continuous, uninterrupted flow of information from the designer's intent captured in the parametric model directly to the manufacturing floor or even robotic arms on the construction site. This minimizes translation errors, it eliminates the need for manual interpretation of often incredibly complex drawings, and it maximizes precision and efficiency in production. It's a truly integrated design-to-build workflow.
And we've seen a really rapid and transformative evolution in the automated fabrication tools that make all this possible. There's been a profound shift towards highly sophisticated computer-controlled machines. Things like CNC computer numerical control cutting and drilling machines, robotic arms for welding or assembly, advanced additive manufacturing or 3D printing. These technologies are now integral to automated fabrication, especially in sectors like structural steel, precast concrete, and the production of complex facade elements or bespoke interior components. For instance, remember those early steel fabrication packages we mentioned, like SDS2 and Tekla structures? They started as 3D layout systems. But they quickly integrated with these machines. They moved from just having predefined parametric object families for connections to supporting automatic connection design. The system itself calculates and designs optimal connections based on structural loads, and then directly sends those precise instructions, cutting angles, hole locations to the cutting and drilling machines. This level of integration allows the incredibly complex, often non-standard parts generated by parametric models to be cut, bent, welded, and assembled with unprecedented accuracy and speed. Designing Reality even discusses a forward-looking technology roadmap for the next half-century of digital fabrication. It talks about moving from teaching easy skills to mastering hard ones, including even making a 3D printer itself. This just shows the ongoing rapid advancement in this field is pushing towards ever greater autonomy and capability in how we make things.
And connecting this to the bigger picture again, the widespread development and, importantly, the increasing accessibility of these digital fabrication tools support what Gershenfeld calls universal fab access and fab literacy. This isn't just about having specific, expensive, high-tech machines locked away in factories. It's about creating an entire ecosystem where the ability to design and produce complex forms becomes more democratized, more accessible to a broader range of designers, builders, even hobbyists. It empowers architects to genuinely envision previously unbuildable forms, knowing that the precision and intricacy of their digital models can be accurately and efficiently realized in the physical world. This, in turn, opens up completely new aesthetic and functional possibilities for architecture. It allows for truly bespoke designs, intricate details, and a level of customization that was previously unattainable, even for the most ambitious projects by firms like Zaha Hadid Architects or Gary Partners. It fundamentally changes what's possible to build.
Now, if you thought parametric design with its dynamic, rule-based systems was exciting, well, here's where it gets really interesting. What happens when algorithms don't just follow your rules to generate a design, but actually help you discover optimal design solutions? Solutions you might never have conceived of on your own. This is the cutting-edge realm of generative design. Generative design basically takes the concept of rule-based systems to the next logical level. instead of a designer manually adjusting parameters, running simulations, evaluating outcomes. It involves algorithms actively exploring a vast solution space. They're searching for potential design options that meet a predefined set of criteria or goals that you, the designer, set up front. This ties directly back to what we discussed about system goals and feedback loops being so critical. You, the human designer, you feed the algorithm the problem. For example, design a building facade that maximizes useful daylight penetration while minimizing unwanted solar heat gain and keeping material cost below X. You provide the constraints, the building footprint, local climate data, maybe material options, the budget, and you define the desired outcomes, the metrics for success. The algorithm then autonomously generates thousands, sometimes millions, of potential design answers. It evaluates each one against your criteria, learning and evolving as it goes, and then presents you with the optimal, or maybe a range of near-optimal, solutions. It's a real paradigm shift, moving from direct creation where you draw everything to a process of intelligent curation where you define the problem and select from algorithm-generated possibilities.
What's fascinating here is how existing technologies actually provide a strong foundation for this already. BIM technology, for instance, already aids engineers in developing multiple alternatives and detailing solutions to a reasonable degree. These capabilities are direct precursors to generative design's broader, more automated exploration of possibilities. But to truly push generative design to its full potential, we need rich input. We need lots of data. And that's where the increasing availability of urban big data and the deployment of cyber-physical systems really come into play. Think of tiny interconnected sensors, sometimes referred to as smart dust, embedded throughout our cities and buildings. These systems create environments that can sense the world, generate massive amounts of real-time data on everything from foot traffic patterns and air quality to energy consumption and structural performance. This data can then feed directly into these sophisticated generative design processes, enabling the creation of buildings that are truly intelligent, responsive, and optimized for actual real-world conditions, as explored in works like The City of Tomorrow.
And the sheer power of this approach comes from its ability to rapidly explore and evaluate so many alternatives. It leads to truly optimized solutions across a really diverse range of factors. A generative process can discover thousands of design solutions, helping to optimize for everything from structural efficiency using the least material possible and minimal material usage, to energy performance, cost, or even specific aesthetic qualities and spatial layouts that you define. This is invaluable when you're tackling incredibly complex challenges, especially in areas like sustainable construction. For example, the book Sustainable Construction discusses the critical need for integrated design. You have to evaluate trade-offs between systems to minimize environmental impact. Think about comparing steel versus concrete structural systems, or maybe optimizing intricate combinations of insulation types, window glazing, shading devices to achieve ambitious net zero energy targets. Generative design can quickly simulate and evaluate these countless trade-offs, often uncovering non-obvious, high-performing solutions that a human designer, relying on intuition or experience alone, might never arrive at.
Right, but this profound capability, this power to explore millions of options, it raises an equally important question about managing the inherent complexity of these self-optimizing systems. As we learn from thinking in systems, how do we make sure these complex, algorithm-driven processes actually achieve their true intended purpose? How do we avoid falling into those rule-beating traps or seeking the wrong goal traps? These are situations where the rules are cleverly manipulated by the algorithm to meet a metric, but maybe miss the spirit of the goal, or where the goals themselves are inaccurately or incompletely defined by the human designer. This can lead to unintended and potentially undesirable outcomes. For example, an algorithm might optimize brilliantly for minimal material use, but create a form that's structurally sound but impossible or incredibly expensive to build, or one that's aesthetically jarring or fails functionally. It highlights the continued, absolutely critical importance of human oversight, ethical parameter setting, and a clear, holistic understanding of the system's behavior. The designer's role shifts dramatically here. You move from specifying every detail to meticulously defining the problem space, setting the evaluation criteria really carefully, and then critically curating the generated results. You have to ensure the algorithms are optimizing for the right things, the things that matter holistically, and delivering genuinely meaningful architecture, not just technically optimal but ultimately flawed solutions.
Okay, let's really unpack this central philosophical debate now, because it's truly at the heart of our discussion about these powerful tools. With algorithms capable of generating so many design possibilities, even discovering optimal solutions, what exactly becomes of the human designer? Does this technology profoundly enhance our creativity, empower us to achieve new heights? Or does it diminish our role, maybe even making us redundant in the long run? It's a big question. There's certainly a powerful argument out there that suggests, especially when you're dealing with incredibly complex systems, the sheer volume of variables and their intricate interactions can simply overwhelm the human mind. It becomes impossible for us to hold them all in the correct order simultaneously, to see all the connections. This perspective leads some to conclude that, quoting from Designing Reality, one has to use algorithms rather than intuitive judgments in making decisions. The idea is that for problems with just too many interacting elements, say, optimizing an entire city block for traffic flow, energy efficiency, pedestrian comfort, diverse programmatic needs, all at once, maybe only computational power can truly manage that complexity and identify optimal solutions, or at least a range of highly effective ones. This perspective definitely implies a diminishing need for traditional human intuition in certain complex decision-making aspects, potentially pushing the human designer towards the periphery of complex problem-solving.
However, that conclusion, as perceptively highlighted in Designing Reality and further echoed in Matthew Crawford's Shop Class's Soulcraft, often makes a critical mistake. It argues from the fact that the mind does not do what a computer does to an assertion about the incompetence of the mind. And that's a crucial logical fallacy, isn't it? Human intuition, human experience, holistic problem solving, they operate fundamentally differently than algorithms. But that doesn't make them inferior, it makes them complementary. As Matthew Crawford points out so well, highly cultivated human minds can get to be pretty good at sussing out a burning building, playing chess, chasing down intermittent gremlins in a car's electrical system, and who knows what else. These are complex problems that often defy purely algorithmic solutions. They require a nuanced, adaptive intelligence, a capacity for pattern recognition based on deep experience, an ability to interpret ambiguous or incomplete data, things that humans still excel at. So it's really not a question of human incompetence versus machine competence. It's about recognizing different, equally valuable forms of intelligence and problem-solving capabilities.
Exactly. My argument, and I think the reality we see in the profession today, is that parametric and generative tools don't replace creativity. They act as incredibly powerful, almost symbiotic extensions of the designer's mind. They profoundly enhance our ability to explore, to iterate, to refine ideas that would simply be impossible or impossibly time-consuming through traditional manual methods. The human designer still defines the initial intent. We set the parameters and the criteria that guide the algorithms, and crucially, we evaluate and curate the outcomes. We're not just passively accepting whatever the algorithm spits out. We're guiding it, refining it, making those critical aesthetic, functional, and experiential judgments that, at the end of the day, only a human can make based on values and context. It actually frees up an immense amount of time from tedious, repetitive tasks like manual drawing or basic calculations, allowing architects to focus on the higher-level conceptual challenges, the artistic vision, and the profound human impact of their designs.
That's such an important clarification to make. What's truly fascinating here, and what many researchers and developers in this space emphasize, is that the ultimate goal isn't to create black box solutions. Designs generated by some inscrutable AI that designers don't understand or control. The aim, as Grishenfeld highlights again in Designing Reality, is to balance the ease of use of the technology and avoiding black box solutions. The goal is to foster deeper understanding and allow designers to maintain control, to push conceptual boundaries with the tools. This means developing tools that are transparent, where designers can actually trace the logic of the algorithm, understand why it produced a certain result. The human designer's knowledge, their vision, their qualitative judgment, their deep understanding of human experience, cultural context, beauty, ethics, these are still absolutely paramount in setting the objectives and making the ultimate choices. The technology becomes a highly skilled collaborative partner, maybe like an incredibly fast and knowledgeable assistant, but not an autonomous replacement. It helps us ask better questions and explore possibilities more deeply. But the why, the what, and the for whom, those fundamental questions still fundamentally come from us, from human intention.
A truly compelling example of this partnership in action is how BIM, just as a foundational tool, streamlines tasks that were once incredibly tedious and error-prone. And in doing so, it frees up human designers for more impactful work. Take clash detection, for instance. This is an automated process within BIM that identifies conflicts between different building systems before construction starts. Imagine a plumbing pipe scheduled to run directly through a main structural beam, or an HVAC duct colliding with electrical conduits in a ceiling plenum. Catching these clashes manually on stacks of 2D drawings was incredibly difficult, painstaking work, and often led to costly fixes and delays on the construction site. BIM automates this, identifying potentially thousands of such conflicts virtually. It also automates coordination between all design disciplines, ensuring everyone architects, structural engineers, MEP engineers is working from the same constantly updated model, no more working off old drawings. And it even facilitates things like virtual hard-at reviews, allowing project teams to walk through the digital model, examine job site logistics, plan construction sequences virtually, preventing potential safety issues or workflow problems before they arise on the actual site. As outlined in the CMAA Construction Management Standards of Practice, these are tasks that, when automated effectively, truly elevate the human designer. They allow us to focus our energy on higher-level conceptual challenges, aesthetic refinement, and most importantly, understanding and enhancing the human experience within the design space.
Precisely. And this reinforcement is just critical to our understanding of the human element in this evolving landscape. Even with these incredibly advanced computational tools, the deep, the sincere, the wholesome aspirations of our people and of our land, in architecture, that beautiful phrase from Louis Sullivan, they still fundamentally require the human touch, the human vision, and ethical judgment to be truly articulated. As Sullivan conveyed in the autobiography of an idea, there are profound aspects of human experience, cultural resonance, symbolic meaning, and just plain beauty that algorithms, at least as we know them now, simply cannot generate on their own. The tools provide unparalleled means to explore, to optimize, to realize complex forms that were previously unimaginable. But the soul of the building, its connection to human purpose, emotion, culture, place that still comes from human intellect, human empathy, and human artistic intent.
So as we cast our gaze forward then, what's next? What does the future hold for architectural design and construction in this era of really unprecedented computational power? How will these innovations continue to shape our built environment and the way we interact with it? Well, one major trend is that we're increasingly seeing architecture understood and developed not just as static structures, but as sophisticated cyber-physical systems. This means buildings and even entire urban environments that can sense the world around them, generate vast amounts of data, analyze it, and respond intelligently, often in real time. It's really blurring the lines between the digital and the physical realities. Imagine buildings that adapt their ventilation based on real-time CO2 levels, adjust their lighting based on occupancy and available daylight, or even reconfigure spatial layouts dynamically based on predicted needs. The City of Tomorrow talks about this trend, highlighting how tiny interconnected sensors, that smart dust idea, can be embedded throughout our environments. They create these digital layers that sense the world and generate data, forming the backbone of truly responsive, intelligent infrastructure. This points to a future where buildings aren't just passive enclosures, but active participants in their environment, constantly learning and adapting.
Yeah, and if we connect this to the bigger picture, this represents a truly profound reorientation of knowledge and power in urban and architectural design. It's being driven by urban big data, those immense streams of information generated by these cyber-physical systems, and an increasingly interconnected digital infrastructure, as the City of Tomorrow really emphasizes. Neil Gershenfeld's Designing Reality, looking even further ahead, offers a compelling technology roadmap for how digital fabrication, and by extension, architectural realization itself, can progress over the next half-century. And it's firmly anchored, as he says, in the underlying science of digital technologies. This isn't just some fleeting trend or a niche application. It's a fundamental, iterative shift in how we understand, design, build, and interact with our built world. It's moving towards continuously evolving, responsive, and truly intelligent architectures. It challenges us to think of buildings not just as fixed endpoints, but as dynamic processes, constantly in dialogue with their context and users.
And to truly harness the immense power of these evolving systems, to guide them effectively, a robust systems thinking approach becomes absolutely vital. It's not optional, really. As Donella Meadows so powerfully teaches us in Thinking in Systems, we have to remember that systems largely cause their own behavior, and also that systems with similar feedback structures produce similar dynamic behaviors, regardless of what the system actually is. Understanding these underlying principles, how different parts of a building or a city interact, how feedback loops can create stability or, conversely, lead to runaway growth or collapse. This understanding is key to designing effective parametric models and generative processes. It means looking beyond individual components to the intricate web of interconnections and feedback loops that govern the behavior of the whole system. It means trying to anticipate both intended and, importantly, unintended consequences of our design decisions within that system. This holistic view is just paramount for shaping complex architectural systems responsibly and effectively. This also inherently implies a need for a continuous process of learning and adaptation. This is actually a well-understood principle in fields like construction management and quality control. Consider the Plan-Do-Check Act, or PDCA cycle. It's a fundamental method for learning from experiments and continuously improving processes. In a computational design context, you might plan by hypothesizing about an action's consequences within your parametric model, say, a change to a facade panel's curvature impacting solar gain. You then do it by running the simulation or generating the new form. You check by assessing its performance against your defined criteria: energy, structure, aesthetics, cost. And then you act by revising your parameters based on what you learned, perhaps standardizing best practices for future iterations. This kind of iterative learning-based approach is absolutely essential for refining these complex digital design and delivery systems. It ensures continuous improvement, learning from both successes and failures, and maintaining responsiveness in an ever-changing world. It's about building the capacity for growth and evolution directly into the design process itself.
And this brings us beautifully full circle, I think, and raises a timeless yet maybe newly urgent question for architecture. Can architecture truly be, as Viollet-le-Duc wondered, an art whose forms are arbitrary, but whose principles alone are invariable? Parametric design offers an unprecedented framework to explore this very question in new ways. It allows us to move beyond a fixation on fixed forms, historical styles, or even arbitrary shapes, towards a deeper understanding and manipulation of the underlying generative principles themselves. The art, then, maybe becomes less about the final form and more about crafting those elegant, intelligent rules, those powerful generative principles that can produce an endless variety of beautiful, functional, and responsive forms, rather than merely copying existing ones or relying purely on intuition. As Viollet-le-Duc's lectures on architecture posed centuries ago, we're now equipped, perhaps better than ever, to answer that longing for novelty and freedom, not by abandoning all structure, but by mastering the very art of the rules. #outro.
Wow, what an incredible deep dive into the absolute cutting edge of architectural design. We've really journeyed from the rigid proportional rules of classical architecture all the way to the expansive dynamic possibilities of parametric design today. We've seen how digital tools like building information modeling provide that intelligent foundation, allowing architects to define systems and relationships rather than just static forms. That's what enables the signature fluidity of firms like Zaha Hadid Architects and Jerry Partners. We've explored how digital fabrication isn't just a convenience, but often an essential necessity for bringing these complex, non-standard geometries into the physical world, creating that seamless flow from bits to atoms. And we've touched upon the really exciting potential of generative design, where algorithms become almost like creative partners, discovering optimal solutions you might never have imagined. And throughout it all, we've wrestled with that fascinating, fundamental question. Are these tools replacing the human designer, or are they profoundly enhancing our creativity, pushing the boundaries of what architecture can truly be? I think we found a pretty clear answer. They empower us. They empower us in entirely new ways.
Indeed. And I think ultimately, whether you're designing a classical temple with its rigid, human-defined proportions and its specific aesthetic ideals, or you're designing a fluid, responsive building generated by complex algorithms interacting with real-time data, the enduring quality of the outcome, what makes it good architecture, still hinges not just on the sophistication of the tools you use, but fundamentally on the intelligence, the insight, and the profound human intention behind the rules you define. So the question becomes, what will you choose to define, and what new possibilities will those rules unlock?
A truly thought-provoking question for every designer, every architect, engineer, builder, and even just keen observers of the built world around us.
Yeah.
Thank you so much for joining us on this deep dive into the fascinating frontiers of design and technology. We hope you'll continue to explore these incredible ideas on your own.